So, do you have a guess of how many coffee beans are inside this canister? So, what is something just outrageously too low? One. Good deal. I like it. Okay, so one. Outrageously too low. Okay, what about something that is high? Too high. 2,500. Yes, I'm going to agree with that. 2,500 is pretty high, yes. Okay, so do we have any other guesses of what it actually could be? So when you talked in your group, did y'all come up with something that maybe is too high, too low, and then something maybe an actual guess, maybe a better guess that we would want to go to the casino and bet on? Uh-oh. You don't highly believe you're 1,000, okay? Good. So 1,000. Any other guesses for actual guess? 763. Okay. 622. Okay. Like it. Any other guesses for an actual guess? 977. 477. All right. Any others? 10?
Yeah.
10. Oh, man. I think I can count 10 on there already. Yeah. All right. So, there are 490 coffee beans in there. Oh my goodness. Holden, I think you were the closest, yes? Were you the closest? 477.
So close. Like too high for the number 2, 500.
Oh, was it? Hey, you were really close to that. You were really close. Okay, so now we're going to apply this to, we call this the squeeze theorem, okay? So, or maybe you've heard it as the sandwich theorem. I don't know what you heard it as, but it is called the squeeze theorem. So let's now look. That's just kind of a fun way to think about it. So let's look at this example. So, what about a limit of finding something that's too low and something that's too high as estimates? So this first example right here says, why do our limit properties that we've talked about so far do not work to evaluate the limit as x approaches 0 of x squared times sine of 1 over x? So not the too high, too low thing yet, but why do our properties that we have done so far not work on this limit? It's undefined at 0. So if I plug in a 0, it's not defined, right? So, and I can't think of anything right now to simplify this. There's no trig that I could simplify. There's nothing really I can do here to make that 0 come out of the denominator right now, right? Is that correct? So, the function is not defined. Not defined at 0. Okay. So let's look at, this is kind of some steps to talk about the squeeze theorem a little bit. So you can use your calculator on this if you would like to, but I want you to think about back when you were graphing in trig, and you were graphing your sine curve. So what two values is sine of x sandwiched between? Or if you're currently in trig, think about the unit circle. So think about your unit circle. So think about your unit circle. So sine of x. So what values of sine when we go around that unit circle? Okay. So what values of sine, so sine of x, are my outputs? So my outputs for sine of x. What are they sandwiched in between? Two whole numbers that were sandwiched between. 1 and -1. Okay? So -1 and 1. Does everybody agree with that? So if you were looking at your unit circle, or remember your trig, your sine curve is a wave like this, yeah? It's beautiful, right? It's a sine wave, okay? So far so good? So I'm sandwiched in between -1 and 1. Okay, so what happens, though, when I say sine of 1 over x? So if I were to think about the same range of values, have I changed anything? Have I changed anything to look at my range of values? Have I changed anything to the range? I may have done something crazy with this, like horizontal, right? So horizontal, it could stretch and shrink. Yes, it's going to look a little crazy, 1 over x there. But remember,
like sine itself can never be greater than 1 or -1, regardless.
Regardless, right? So no matter what, okay, this sine of 1 over x can never be greater. The range of values is always still going to be -1 to 1. Yes? Do y'all agree with that? So nothing's changed. So the range of values for sine is always going to be in between. So the range is going to be in between -1 to 1, no matter what. Yep. Okay. So now let's think about what happens if we stretch it vertically or shrink it vertically. And that is multiplying something on the outside of the function. Okay. So remember, it was our a value that we talked about a lot in foundations. We'll graph in trig very soon. So it's also your a value. We talk about it as a as well. So it does vertically stretch and shrink same way as if we were doing just a basic function. Okay. All right. So what happens now to the range of values when I multiply by 3? So what happens when I multiply by 3? So multiply everything by 3. So everything gets multiplied by 3. So -1 times 3 is still going to be a -3. 1 times 3 is going to be a 3. So my range of values now is going to be sandwiched in between -3 and 3. Yeah? All right, what about the next one? What about 1/2? -1/2 and a positive 1/2, yeah? All right, what about k? -k to positive k, yeah? Okay. All right. So let's talk about using the same idea. Now what happens when I have a x squared? So the only thing that's changing right here is a what? Okay, and you're squaring the x, right? So it's going to be an x and you're squaring it. So what's going to happen to the range of values here? So I'm still going to have a what? -x squared and a what? Positive x squared, okay? So what this is telling me and what we're about to show is that x squared sine over 1x is going to be sandwiched, squeezed in between these two functions, -x squared and a positive x squared. All right, so let's think about something real quick. What does -x squared look like on the graph? If I were to graph -x squared, what would it look like? It would be an upside down parabola. Perfect. Okay, so it looks something like this. Yes. So this would be my -x squared. What would a positive x squared look like? Parabola. It would be a right side up parabola. I'm not going to be able to draw those very nicely. I'm sorry. Almost. Okay. So what do you think if I then look in the middle of the sine 1 over x times x squared? What do you think that graph is going to look like if you were to even graph it in your calculator? I'll give you a hint. It looks kind of crazy. It's something like this. Yes? It looks something like this. Okay? All right, so when it says find the limit as x approaches 0 of the lower bound. So what is the limit as x approaches 0 of your lower bound? So the lower bound is going to be the what? The negative x squared. So what is the limit as x approaches 0 there? It's just going to be 0. Perfect. What about the limit as x approaches 0 of your upper bound? So this is my upper bound, yes? So my upper bound here. So what is the limit as x approaches 0 of just x squared? Is also going to be a 0. Okay. So what is now the limit as x approaches 0 of x squared sine over 1x? Can it be? So when you took the limit over here, yes, so that you took the limit of the lower bound. Yeah. And you told me that that was what? 0? You took the limit of the upper bound and you said that that was also what? Well, how in the world, if that's an order, yes, if that's an order, what do I have to be? What does the middle have to be? 0. Perfect. Okay. So this is the squeeze theorem. Squeezing. We are squeezing the function in between two other functions. Okay, so we have an upper bound and we have a lower bound, and we squeeze it in between. So if the upper bound and the lower bound are the same, so if the limit exists at both the upper bound and the lower bound, if they're the same, then that says that the middle one has got to be squeezed in between there. So it's got to be equal to whatever the lower and the upper bound are equal to. Yes? Okay, so let's put that in kind of a formal definition here. So we've got 3 continuous functions. So if f of x, so let's call it f of x, g of x, and h of x are continuous functions. On some interval containing the a, and we can say that g of x will be our lower bound, f of x will be our middle, and h of x will be our upper bound. So let's do that. So on that same interval. So that just says the order of how the functions will be. Okay. So basically the f function is going to be sandwiched between your g and your h function. So it's in the middle. So we're talking about the y values of each one of these functions. So your g is your lower, your h is your upper, and f is going to be in the middle. Okay. So if the limit as x approaches that a value, so where it's continuous on, of g of x is equal to the limit as x approaches a of h of x, if those are the same value, then by the squeeze theorem, so this is just kind of the formal definition. So by the squeeze theorem, the limit as x approaches a of the middle function f of x is now going to be equal to that same limit, that same L value. Okay, so what happens when the lower and the upper bound, the limits are not equal? Can we apply the squeeze theorem? We cannot. Okay, so they have to be equal to the same number for this to apply. Okay, so to check your squeeze theorem, you're first going to check that the conditions hold, that it's continuous, and that then we have an order of our functions. So we've got g of x is less than or equal to f of x, which is less than or equal to h of x. Okay, so we have to have those conditions applied. Okay. Then we identify the upper bound function and we identify the lower bound. Just like I said, g of x less than or equal to f of x, which is less than or equal to h of x. Okay. And then we evaluate each limit of the upper bounds and lower bounds. If they're equal to each other, then we can conclude that the squeeze theorem applies. Good deal? Does that make sense? Sure? Okay, so take a second and answer number 1 on the back. Number 2 is just kind of formally putting together what we did on the front, so I'm not going to go through that one again. But look at number 1. When you looked at your graph, just on the interval from -1 to 1, which functions were your upper and lower bounds? So which one fell in the middle? So what was your lower bound? Which one? Cosine of x. Okay, perfect. So your f function would be your lower bound. So is your cosine of x is your lower bound. Which one was your upper bound? Was the straight line 1? Perfect. And then the middle function that was squeezed in between those two functions was sine of x over x. Yes? Okay. So there's a beautiful proof to this that I don't think I've got time to show you, but it's talking about the area of each one. If you were to draw just sine of x and draw some triangles, I will be happy to share with you that beautiful proof. It's really nice, like area of each part, and how this kind of gets, how I chose those functions. Yes, how I chose cosine sine x over x and just a 1. Yes, where this came from. So if I were to now use squeeze theorem to show that the limit as x approaches 0 of sine of x over x is indeed equal to 1, what would I do? So you already first proved that sine of x over x is sandwiched in between two functions, cosine of x and 1, right? Okay, they're continuous from -1 to 1, so those conditions all apply. Are y'all good? Okay. So now, to use your squeeze theorem, you will take the limit as x approaches 0 of cosine. Yeah? What is it? What is the limit as x approaches 0 of cosine? 1. Okay, I'm not going to find the limit here because I'm using squeeze theorem to show this. What is the limit as x approaches 0 of just a 1? Is a 1, indeed. So that means that the limit as x approaches 0 of sine of x over x has got to be sandwiched in between 1 and 1. So therefore, what? By the squeeze theorem, by squeeze, the limit as x approaches 0 of that special trig function is indeed equal to 1. It's pretty spectacular. The proof is kind of fun too. Okay. All right. So like I said, number 2 was basically putting what we did on the front page all together. So let's look at number 3. Did y'all get to number 3 yet? Or do I need to give you a minute? Minute? I can give you a minute. We've got time. So if it says if f is a function that satisfies k of x is less than or equal to f of x, which is less than or equal to m of x. So it's telling us that it satisfies one of our conditions already. Yes, so it is sandwiched. How about that? My y values are, bless you, are in between k of x and m of x. Yes? Okay. So how can I evaluate and try to figure out the limit as x approaches -1 using my squeeze theorem? Okay. So I need to evaluate the limit as x approaches -1 of k of x and the limit as x approaches -1 of m of x. And we hope that they are what? The same number, right? If they're not the same number, then I can what? Not use it, right? So squeeze theorem does not work here if they're not equal to the same thing. And I hope that's what it is, right? Because I said not. Okay, so if we find the limit as x approaches -1 of my k function, what was that? So it's -1 squared, -1. So -1 minus a 2, -2, so plus a 2. So that's a what, 4? Is that right?
Yes.
Check my math on a Monday, please. The limit as x approaches -1 of m of x. So -1, positive 1/2. 14, 7, 6. 6. Okay. So what happens? They are not equal to each other, so I can't use squeeze theorem to say there is a lot of other values between 4 and 6, right? So it's not exactly at one value, but there are a lot of values from the lower bound of 4 all the way up to that upper bound of 6. So I cannot use squeeze theorem to show that I can evaluate the limit as x approaches -1 of that function. Good? All right. What about number 4? So I've got a table of values. I've got f of x, g of x. It says that they are what? Continuous, so it's already given me one of my stipulations there. It also tells me that if f of x is less than or equal to k of x, which is less than or equal to g of x. So that means my lower bound is going to be the f of x. The upper bound is going to be my g of x. Oh, is that thunder? Or is that a train? That was thunder, okay. Okay. Or a truck. It could be all kinds of things these days around here. Okay, so what happens if those two things are going to the same value? Then can I find the limit as x approaches 1 of k? Can I squeeze it in between there? Okay, so let's look at it. It's continuous. So as x approaches 1 from the left and as x approaches 1 from the right, so for f of x, it's going to be equal to what? 11. For g of x, it's also going to be equal to what? 11. So therefore, by what? By squeeze, yes. I'm going to shorten it there. So by squeeze, the limit as x approaches 1 of k, even though I don't know what the function is, it is going to be equal to what? 11, because I already knew that it was my middle function value. Yes, so it was in the middle. Does that make sense?